but inside actually the Excel file, you can link directly to the data. Okay. So what are the data? Okay. Let me see. Yeah. I need to go into my assignment. We can. I need to find ways to sum in my computer, so it will be easy. My computer is under C. So when you download this software from NRL, you can create. Because I have several versions here. Sorry, there's a special. Okay, so whichever is your, when you download it, you will have a sum directory when it's downloaded in your PC. You create this EPW folder, right? And in this folder, you will put your solar data. Solar data, when you download from that location here, so these are for Australia. I believe there's also for Singapore. I choose from here. So what you're doing is you will have a location, right? And now I pick up one random. It's a zip file, and there are different formats. We extract this EPW file, right? You extract and then you put in that folder. So that's a very fast thing to do. So you will choose one set of data, and only one location is enough, based on one of the two students. And then once it is installed, and then you can do your data analysis basically using SAM, because you see SAM. Okay, so you know how to download it. That's really easy, right? So there is a version for PC, there is a version for Mac if you need. My suggestion, use the, my version is, the one that I'm using is November, okay, it's written here, November 22. There's obviously there are new version, but every time there's a new version, slightly different things, so it takes time to find maybe difference. Maybe it gives you some, little error. So if you use this version, you can run the example I put on the website on Canvas. In fact, in Canvas, I put an example of file which is based on my case study that I gave as a PowerPoint presentation to you. You see, you have a PowerPoint presentation here. So what is this? Residential application where there are two add-on. So okay, this one is just a PowerPoint presentation, and this is just an extended written form of the presentation, so like a lecture notes. So all the information is there. But here you can see I also put this example of SAM already set with this location, Melbourne Olympic Park. So I use this for my case study. You will have a different location for your case study. So my suggestion, download this guy over here. This example included the data file, just initially to try to get to run that same example I'm showing. Then you will change your data file. So you will change your data, you will change everything else, right? But because it's just easier that if you start from scratch, maybe there's some things just different. So in this way, you just modify this one, okay? Okay, so basically what we are doing when we use SAM, we use the PV battery residential, okay? If you start from scratch, let me start from scratch, right? So let's suppose you do a new project. I don't say this. So what you do in your project, not photovoltaics, energy storage, and then you do detailed PV battery, residential owner, and that's it, okay? And this is a new one, really, right? But as I said, you can start from scratch from 0, or you can use mine and just change that one. So up to you. But I'm just telling you what it is. It is storage, because we need to have a button. So yes, no, and then I'm going back to my one. Sorry, it's going here. There you go. So it will complain a little bit at the beginning when you open up, because it will ask you, oh, why you don't install the new version. Didn't complain. Oh, you see, it does that. You just ignore it, move like, cancel, don't update. It's okay if you want. If you're really brave, you can use the new version. Just that sometimes they change things, and the settings may be different, and you need to sort out the setting. It's nothing difficult, but why you want to, get in trouble, right? No point. Okay. So then, first you have to do location and resources. So then, basically, you will have your own file. You just go on this side. If you want to change location, for instance, another location in Australia, I'm using this one. So you just click that one. So when you click the one, it knows that you're looking at this, and it is importing all the information here. You see the latitude, the longitude, the time zone. Because he needs this information to do the simulation, etc. Global, horizontal. You see annual average calculated from weather file data. It says that the global horizontal is 5.15, direct normal 5.38. These are all peaks and hours, right? And so on. So it calculates a lot of things. In particular, view data. Okay. So these are the the data actually, are data for that location, solar radiation. And you can see that it gives you the direct normal radiation. Remember, the direct normal radiation is normal to the collector, the diffuse irradiation, and the sum of the two, global irradiance. So basically what you can do, these are the on horizontal surface, okay? But generally we use the collector tilted angle, right? So then what you're doing, you download this data, okay? You just click with and here you can say data to Excel. And it creates for you an Excel file with the data here. Exactly from that file. So it's good because we have all the data. Fine. At this point, what we're doing here, we want to convert this to the tilted surface. We want to know basically what are the peaks an hour for each month on the tilted surface. So now, probably to do this, I just follow the example here. What we need to do is, you see, these are the raw data as downloaded now. We want to construct this other figure. This other figure gives the daily average daily global irradiation in kilowatt hour per square meter. So I want the peaks an hour for each month. And you see this is the horizontal collector, and this dark blue is the tilted collector. And then also the temperature. Actually, the temperature, you can also download the temperature from the file data. I forgot about that. You just need to look here. Temperature is here, right? Is the not the dry bulb temperature. Okay, the dry bulb temperature is the ambient temperature. you can use this as ambient temperature. So you have all the information you need to do this, for him to do the simulation, but for you to understand the data file is somehow. Yeah, actually you could run this without doing all this stuff, but it's for you to understand what's happening, okay? So when you have your data file downloaded from SAM, you can use another, here I give you this example of solar radiance at theta arbitrary angle. This is what it calculates the other graph. Okay, so it's everything done. So you just need to input your data in there. Okay, so now let's look for that. I need to go to maybe here. No, I don't have the file here. You know, I can download from online, but I don't want to download because I have already, just need to find where it is. Okay, it's under here. I know that it's here. So, because this is done before. 6. Okay, so should be this one, right? Okay, so you open that file that is there, you download it. So slow. Maybe I have too many to open. Yeah, makes sense sometimes when you have too much happening. Yeah, sorry, I forgot I need to close something. It's slow. Let me close. Sometimes, yeah, I have too many things open. I just end the Excel. Also this one. Maybe also this one. I didn't know it was open. Okay. Sorry. I'll go back to Excel now. Okay, so this is quite an enormous file, but it's quite simple. Alright, so you start from here, right? So here you're gonna put your location. For me is Melbourne. So latitude angle of your location, right? And here it just calculates the latitude angle in radians. Then here you see you can adjust those one, right? So you know, here I set that at latitude angle and azimuth angle 0, only towards south. So I'm north, and you're going to do the second because it's still a location in the southern hemisphere. Here, when you download your data file, this is just the time. So you can leave like it is, or you know, somebody asked me, can I put for starting from 0.5? That's fine, you know, it's not a problem. Basically, you can copy the data that you download from SAM in this area in green. Okay, so green is the data new that you want to copy inside this file. So this is the global irradiance, the direct normal radiance, and diffusing radiance. You just copy from when you download, you copy in the green area. So in the blue is calculating, things, okay? So here. And then after that, it will plot your data. Okay, so this is just the plot data that also some does, but a little bit better format, together. This is the temperature plot as well. So the temperature, okay. In this second region here, you can copy the temperature as well. So the data from the temperature.
So the tilt angle, do we leave it as the one that you have keyed in, or do we change it? The tilt angle.
The tilt angle you have to change, yeah. So basically, in green you copy the data, right? So the temperature data, the global temperature, and then in blue you calculate stuff. Okay, so, and then also here there is the monthly drive up temperature. This one you can copy, because you see here, you can also get the monthly value and just copy this one here from the temperature, right? Because yes, this is not giving you the tilt angle, it gives horizontal. You want to transfer it to horizontal plane, but the temperature doesn't matter. Temperature is the same, so the native. So if by copying green all this stuff, the monthly value, and blue is calculated. So that's all, and that is finished. So remember, okay, copy inside here, and copy the graph now in this other region, okay, in green. Actually, this one probably you don't need to copy, because oh no, yes, also this one. And what it does, this Excel, well, it obviously generate the graph, and what is important is this graph here. I want to have this graph here, right? Because this is the graph that gives me the value on the tilted angle. So if you see what happens, right? If I go back here, instead of tilting at 37, if I tilt, I don't tilt it. On the tilt, not very interesting. Let's tilt just 10 degrees, okay? So you see, if I tilt 10 degrees, the difference is very, very little between the horizontal and vertical. You can see more on this, actually. You see this is a graph that is much more clear. So this one shows the irradiant and tilted plane and horizontal plane. If it's only 10 degrees, it's almost the same. If I tilt at 60 degrees, so it's kind of different, right? So that's what does the effect of collector. So we put, if you want to know what is the best, actually, the way is to sum all the value on the tilted collector, and then you find what is the the tilt angle and give you the maximum collection, right? Generally, it's close to the latitude angle, just a bit less. So here I put, you can put close to the latitude angle. So, but anyway, you can play with that and find out what is the best if you want, right? It's up to you. I mean, for instance, if you put here, sorry, it's here 37, and the azimuth angle actually is better 0. If you put 180, which is completely wrong, right? You can see that the effect on the it's very bad, so you don't collect anything, okay? So the red is your collection. So, but anyway, this exercise is to, you see here, we are wrongly oriented our collector, we lose the radiation. So if I orient it towards south, the sun doesn't go on it, it's blank. Yeah. Yes, it will be facing always against the sun, so it doesn't get any sun. So this calculation includes also diffuse radiation. Okay, so it's all explained what it does, but you can just use it, yeah, as either your presentation and here and calculated things. All right, so then after you did this, basically go back to here. What you're interested in to have as yeah. Yeah, you can tilt it a little bit. You're not always, straight north. You might be dependent on the location of your house. Yeah, I mean, if you are just off the direction of the equator, you collect a little bit less. If you are 100 degrees off, it's completely off. Yeah. So, yes. So at the end, what you want to know is this value here, right? The daily irradiation on a tilted surface. Okay. So and then basically you have your graph. These are the raw data. These are the data manipulated to have the value on a tilted surface. And then you have your final table showing you see by tilted at the latitude angle. I have a peaks an hour of 2.8 kilowatt hour. Yeah, 2.8 peaks an hour in June. So really at latitude angle I increase my collection during the winter and on average during the year. I lose a little bit of summer, but so in Singapore, I don't know actually, would be nice to do Singapore, but we're now busy to do Australia. But in the future, if you want, hopefully this will be available for free for perhaps a few years. So if it happens in your job, you can use this tool and do your own calculation. It will be fun for Singapore. Because I'm pretty sure you can look at Singapore as well. There are some data for Singapore. Okay, so basically this is the solar resources part. Yeah, so the solar resources are just this. Now, let's go to the next point, right? So next point is actually to do the sizing. In here, it would be good to have an idea of what is the household demand in terms of energy. So this is called energy audit of a household. So what you're doing, you list your appliances. You don't have to go very detailed, right? Simple, because we don't, just the major thing that you need. The power, how many you have. So roughly you have an idea of how much your load is in electricity for each season, right? There's 2 seasons, not do every month. So unfortunately, again, this is a bit strange for you because it's for southern hemisphere, and then you need to think of winter is a different period of the year. That's a little bit tricky. But for us, it's obvious that June is winter, but maybe for you it would be a little bit strange. But anyway, try to think about maybe you're gonna come to Australia and work there. Obviously, if it was here, it would be slightly different, right? So it's very, very location dependent, this stock analysis. So anyway, you come up with your energy demand for each month, okay? But you can see those values are always between 20 and 30 kilowatt hour, a little bit more than 30. For instance, in Singapore, you would use a lot of air conditioning. So actually, Singapore, the electricity demand would be quite high. So you don't have heating, but the air conditioning is high. Expensive. The electricity bill must be high. So Australia, no, because particularly in Melbourne, actually the cost mostly winter because of the cold. And then particularly if you're outside city, then the temperature tends to be quite low. Therefore, typically for Melbourne, the temperature, the auditing, for other area of Australia like Queensland, no, the air conditioning becomes more relevant, not as bad as Singapore, I think. The temperature much lower, not that humid either. So anyway, depending on your location, try to figure out what are those values to put in here, okay? And yeah, it would be a bit difficult for you because you don't know the place, but I linked you with a lot of material that you can have a look at and do your findings about the climate zone that you are looking for. Obviously, so Australia will be different zone, like Queensland, Western Australia, South Australia, and south, the area of Melbourne. The climate is slightly different, right? So Queensland tends to be sunny, very sunny, very high. If you are lucky, you get the Queensland location. Your approach is beautiful. If you get in Tasmania, they probably want to change the type of renewable energy. Say sorry, I want a wind or hydro, probably better, right? No sun, not much sun. Melbourne also is not great for sun because when there is, it's good. But it's very unstable, so you can have, because actually it becomes, because the sky is very variable, there are a lot of clouds, they come and go. And so you might have a very hot moment and then all covered, so when it's covered, it's not good. So anyway, you can look at those information there.
We use our own house appliances details, right?
You can also use your own that you have at home, really. Your own bill, except that for Singapore, your bill would be very dominated by the air conditioning. I have no idea what is the load here. Because the houses would be smaller, so less to cool. Because if you have something big, it would be expensive. I have no idea the cost of electricity in Singapore either. Yeah, it is a study. I think I'm gonna write a paper on this. But yeah, so you can use as an example your appliances, right? It's just to get used to this kind of analysis. Then what happens once you have this table here? You create this table here. You can import that in SAM. Okay. Okay. Now let's move back to SAM. All right, so this part in SAM is electric load, okay? And this, you see it's in here, right? And so you just look monthly. So here, monthly value, any value, you see you can put them here. Just copy and paste. If you have an Excel, just copy inside there and that's it. Okay, so January is the total of the month of January and kilowatt hour that you need. So 701, whatever you get is the number you get here. Okay, then you can scale electric load to profile. Tick that box here. What does it mean here? This means that we have an electric load profile, okay? So one thing is say I need 700 or 800 kilowatt hour in a month, but how much I'm actually consuming every hour? Think about it, it's a different problem, right? What is the load profile? In fact, the load profile that I gave you as an example, I took a load profile of a house in Sydney. So I didn't have a load profile for each location, so we just used that one. But really, this is also very much dependent on the load profile that your house has. And this depends a lot on the location, on the habits of the people in the location. Of course, during COVID, people were staying off, so the load profile was totally different, right? Now we're going back to the north. But what happens typically, you have a load profile. Let's see if there is more details here. No, we can look in SAM. So what you're doing here, you first of all you can load import. Okay, it's already imported in mine. you know, if you had to do, you would import exactly the file that I put in there, which is a text file called bankstyle. That's it. Yeah. But you also don't need that because you can create your own profile by you see calculate load the data. Here you see here you can calculate your load profile by the house that you're having. Okay, and it's I mean. I just decided to input that one because it's simple. And then you can view load data, which is this. Okay. And you can see, for instance, you can zoom in. This is you can zoom in here. Let me see. I think maybe you can do. So this gives a view of the profile, typical profile during January, typical day. So what is showing here that during the day when you are actually using the load, okay, which depends a little bit on the month from this price. So. Basically, you have a peak at this point here. That's where you maximally use the electricity. Okay. Anyway, so this is just the when you are actually consuming this electricity. It's not just the total. So it's scaling to your monthly value, but you use that profile. Anyway. That's all. So there's not much to do here, it's only to input your monthly value. Okay, what next? So then, okay, we need to choose the module. And here we are. So we go back to module. And here you have a lot of modules, so you can choose whatever you want, really. But each module, you will have the information about the nominal efficiency, the maximum power, all the things that we have studied, okay? So you can, for instance, look for a module that has a high efficiency, which would be monocrystalline silicon. This one, for instance, I choose is a multicrystalline silicon. And then you can see also what is the temperature coefficient. So all this stuff we just use in the manual calculation, right? So and exactly what. So I just put some information in your report about what kind of module you are using. Also, it's a good idea to use something not too small, like I mean this 300, like not use something. I think they are all pretty big. This module, it's between even up bigger, right? So anyway. You can see what you like it there quite a lot. You choose one of them, right? So it's not really important which, but you can inform in the report. Then there is inverter. So this is the most difficult part, to choose the inverter. How do we choose the inverter? So let's look at, so in your report, they say you will talk about this. So here I just, what I got? Okay, so these are just settings to do, but if you use the file I give you, this setting already there. It's hard to read here. Nominal, okay, so it needs to know how to do the temperature correction, so we do with the nominal operating, so the D-rated temperature method with the nominal operating rated temperature. You can do also with using heat transfer, right? It's just two different methods. It has embedded the calculation to either one or the other. And then mounting, it's mounted, etc. If you use mine, you just leave as I did. If not, just make sure if you start from scratch, you need to set those things, right? Otherwise, it does this calculation a little bit different. Because I didn't explain the heat transfer, so I just don't know what it does, right? So we know what it does with the nominal operating temperature, that's all. and just because it's familiar. Now let's go to the what is the size. So to size roughly the inverter, what we need to do is to look at what is my design month, right? So I decided to look at June. So in June, I saw that I have 24 kilowatt hours per day of energy demand, and I have 2.8 peaks an hour, right, from that graph in June. Then I assume that I have a 0.75 total derating factor, and I calculate how many modules I need roughly. I know what is my module power because I've just chosen. So my case was 325, you would choose something else. I have my peaks an hour, total derating factor here, daily, and roughly I calculate that I need probably 42 modules, right? Roughly 14 kilowatt. Okay. Then what means that I need to look for inverter roughly that power. So your inverter is roughly the power of your PV system, power-wise. It can be slightly lower. Okay. It can be slightly lower. Why? Can you tell me why it can be slightly lower than the system power? Think about that. Because an inverter, what does an inverter? An inverter convert the power, which is DC, in AC, right? Because your appliance, they work with the alternating current, while the photovoltaics produce direct current. So obviously the power needs to be close. But why the inverter can be smaller? Because first of all, why we want this inverter smaller? Why we want? Because it costs less, right? Think about money, right? You pay for what is the power of the photovoltaics and the inverter. So if the inverter is too big, for instance, more than 10 kilowatt, that goes into a different set of cost than something below 10 kilowatt. Okay. Then okay, what to spend less? Then can I make it smaller? Yes, because the maximum power of your PV will never be reached. Because it is achieved at temperature which is never happening under the sun, particularly under peak sun. So you will work always slightly low. So you can afford to have an inverter that handle a little bit lower power. How lower? You can go even 30% lower. Not more than that, because then you start cutting. So it doesn't invert, and you're not able to work when the power goes up. You can't convert it. Okay. All right. So therefore you can look for an inverter which has roughly. So I was thinking about 14 kilowatt. I look for an inverter of 12 kilowatt here. Okay. It's still big because my system is gonna be big. Manual is not very good, and so it's quite big inverter. And let's see. Once I choose inverter, then I need to look at what are the properties of this inverter. So the DC nominal voltage, okay, is 370 volt DC. And then I need to look where it's operating, which voltage is operating, between 480 and 300 VDC. So that's what I need to set up my series and parallel for the photovoltaics. And then I simply give you some guidance here on how to size it. And again here, I provide you an Excel file to do that. It's called, oh, sorry, I went with low, okay. That file is called, breaks down, okay, so all in order, okay. It's called PV number of module sizes. Okay, so this one is you can use just to have an idea of what type of system you're gonna make it. Okay, so let's open that file. Is here. So here you will set the VCC, which I mean this is the it's a kind of it's a voltage that you assume is gonna be the voltage you controlling the battery. Because you have also a battery, don't forget about that, right? So when you have a battery, the inverter also has a charge controller to avoid that the battery is overcharged. So let's say that we set 420 because this is a value that is good. It's kind of midpoint between 300 and 480, which is the maximum range of operation your inverter. And also, actually, this is a maximum power point controller as well. So I put it at 420 here. Then you can assume that you have your PV on the roof and the inverter may not, it's not on the roof, it's not generally. So you have some cables, so you have some losses, which can be 0.93% losses. Okay, it's a default. You can use it as a default value. So then this is the voltage at the PV system. This in blue is calculated from the above. And here you put the maximum voltage of your the module. Okay. Remember this. You can read from the module system here. Module. Here you have maximum power voltage and maximum power current, okay? So these are the values you need to put inside Excel. So maximum, module maximum voltage. And so here it calculates how many in series, obviously. So the series will be the voltage of the PV system divided the maximum voltage of one module, right? So here I found out is 10.3, so it means I can put 10 modules in series. Then here you put the VDC of your inverter, nominal VDC of your inverter, energy daily that you just calculated before. Backup days, okay, here, because we have a battery, right? So what's for, okay? So battery, if you have grid connected, really, maximum is 1 day of storage, yeah? Generally the battery is used only for storing some electricity when you overproduced, and you can send to the grid and store in the battery. And use when the peak demand so that you save energy from the grid. So it doesn't have to be a lot. So here I choose 0.3, you can store a little bit more than that, that's 30% of the time, or during 24 hours, so it's about 7 hours of storage, but you can increase it, up to 1 day. Obviously, if you go up, it becomes really big, and so I put 0.3. Here you put the inverter efficiency. Again, this is something you can read on the data sheet of the inverter. I think mine was 0.3. Depth of discharge, this is very important. This is for the battery, okay? So if you have a good battery, you can afford the depth of discharge much higher, like maybe even up to it's maximum 80%. You can afford 60% for lithium-ion battery. If you have cheap battery like lead-acid battery, then you wanna, because they will die, before the 20 years, and they will be unusable after 10 years. But yeah, you can push them up to 0.4 as a depth of discharge, because clearly, if you keep this low, then the system will be bigger as well. So anyway, and here it calculates for you the battery size in ampere hour that you need for the system. Here you have the efficiency of the battery, and this stuff that calculates. This one at peak sun hour design month. You have to input this. Sorry, this should be in green. You need to it should be in green, this one, because it's an input value. Okay, so I use green for input and blue is calculated. Then this calculate the current and the photovoltaics. This is the module maximum current. Also, you need to input. Fuse rating. Okay, so here maybe you don't find this information. It can be 20 or 15 ampere. 20 can be used as a default. It depends on the standard. For in Australia, it's 520 ampere. And here it tells you how many strings. Strings are you put in the module in series, like in this case a 10. Each of this series is one string. Okay. So here we say that we have two strings. Always, if you can, always round down. Okay. And this is Paris in parallel. I round it up because if I round it down, I can also round down, but then my system may become a bit too small, 20 modules, but I want to round 40. So I wrote 2. And then so basically I have 40 modules in total. So at the end your size is to be done based on electrical parameters, not just the energy balance is good, but then we have to cut those cables, right? And it makes sense, and it doesn't explode. So roughly we need to have those that. And so therefore at the end here you have about 40 modules, and it calculates your final power. Yeah, I just put some losses, so you can use it the same as the default. Okay. So what you need to change are probably this value where you want to control your charge, the voltage you want to control, and your module maximum voltage as well will be different module by module. The VDC, this will be different, so the depth discharge may be slightly different. There are a few things you can change in your project, okay, compared to mine. And then, okay, so in my case here, so you see that the string is, what is called string is this. So, it's shown, okay. So the string should be straight because here it seems to be. So this is this one string, so you have two strings in parallel, and then these two are. This is a fuse here, right? A 20 ampere to limit current, and then another group of two strings in parallel. So for a total of 40 modules. Okay, and the voltage you have here, current, is calculated by the little Excel file. This is just to give you an idea how to do the sizing. At this point, then you're fine. Right? When you are sorted here, you're pretty much done. Not much else to do. Then you basically go. You have inverted design, system design, and here where you have to input you see in modules per string I said 10, 2 in parallel, and then 2 subarray for a total. So you have to set up this here for 40 modules. So your one could be different, right? So I don't know. Yeah, so this one has to be set slightly different. So you can have more, or you can have less. Organized in different way. You can put more in series, more strings in parallel. Yeah, so it depends on your parameters, electric parameter. And here you can see I'm getting a DC to AC ratio of 1.1, means that my inverter about 11% smaller in power. So it's okay. I have only one inverter. Then here is the tilt angle. So I tilt at the latitude here. Here is the ground coverage ratio. You can use 0.4. This is for the self-shading, right? So this parameter is linked to the self-shading, which means the minimum distance between the two arrays, two sub-arrays, to avoid that there's shade from one to another. Yeah, so this can probably be 0.3 or 0.4, depends. You can use 0.4. In fact, here there is the shading part. And yeah, also here you need to set up that. Aspect ratio 1.5 is fine, doesn't matter. Yeah, so here it basically calculates the row spacing, okay, automatically. So basically by changing this this parameter, it calculates different row spacing. I mean, I explained in my slides what does it mean, right? In practice, it's very simple. Actually, we need to do it immediately soon. Yes, we have time. So, but yeah. So basically, this relates to the theory. Let's see, for the shading is this one, right? So if you have let's say two array, right, or photovoltaics, you need to put the second row far enough for the first one, otherwise there is a shade from the certain, during maybe in the winter, right, so which is the longest, right. So then here there is an explanation how to do reduce the self-shading. So how to calculate the distance to avoid self-shading. So roughly does the same thing, but he used a different way of using this parameter, which is called ground cover ratio. Means obviously if the ground cover ratio is very high, means they're very close to each other. Okay, because it's a number between 0 to 1. So if it's 1, it means that maybe attached. Yeah, not good. So if it's more, it means they're far apart. And you can see from some dots, but it's the same. So but basically what I did here, I just calculated the row spacing of 4.2 meter for my case, and then I set up that ground ratio coverage about to give the same number this time. So it's you see 4.375, and I calculated 4.2 meter. I'm happy enough because if I change this, let's put 0.5. You see they become closer. Okay, so that's too close probably, and what I use 0.4, maybe 2, I don't know. Okay. Yeah, 4.2. Okay, so that would be just adjusting that one and just the separation between the rows. Okay, losses, you can leave the one I put here because losses are to know. So I put some standard losses. They can be slightly increased if you want. But battery, okay. So there's a little bit of setting here, but again, my battery is desired by capacity is a 30.6 kilowatt hour. Okay, where does it come from? 30.6. So the energy to battery. It's a bit bigger now. Okay? So the battery energy capacity in kilowatt hour should be the product between the battery ampere hour and the VDC. Okay, I don't know why I wrote here 11.5. Maybe this one is not up to date, but energy to battery. So the battery here is battery ampere hour is 79.4 multiplied by EDC, this 370. Whatever it is, the number is the kilowatt hour. $30.6. I don't know why I have 11 point. Yeah, maybe. You see, battery per hour is 29.8. It should be the same number here. Battery per hour, 179.4. Should be 29, so what's it should be 30.6 in this example here, so 29.8. But anyway, here you can see the formula to calculate the ampere hour and the battery capacity and the ampere hour multiplied by VDC. So I'm not sure why it's not matching. So anyway, I calculated for this example that my battery should be 30.6 kilowatt hour. Yes, just a bit. It's here it says 29. Sorry, I don't know why it says 29. It should be the same. Ah, okay. 29.6. It should be the same formula that there. So. But anyway, it seems to be right. Okay, let me just check. VDC. Discharge. So 79.4 multiplied by 370, how much is it?